Thanks. Thank you so much. So Jonathan and I are happy to be here, and thank you for inviting us. And also to tell you that Jonathan and I are working as part of a bigger team at Western University. Western has funded for 2 years now, work in developing resources in AI education. So Mike Kajabal, who's in computer science, is the lead of the project. Also, as part of that team is Immaculate Namukasa from Western, Jody Williams from FMI EAO, and myself. And also we have a large group of graduate students like Jonathan, who are working with us. Jonathan and I have done quite a bit of work together, and I've really enjoyed that. So today we're going to be talking to you about mathematics and mathematics education and artificial intelligence. And there are perhaps two, oh, by the way, these slides are available at that link up there. So bit.ly/AI-fields. I think the AI has to be capital to get it, but you can try it either way. So there are perhaps two interesting directions to investigate. One of them is AI as a new literacy. And we don't mean literacy as something to study, but literacy as DeSessa defines it, as the adoption by a large cultural group, perhaps an entire civilization, of a particular infrastructural or representational form for supporting intellectual activity. Like, for example, algebra was at one time a new literacy. Imagine doing mathematics without algebra. So imagine doing engineering without computer science. Imagine doing, in 10 years from now, whatever we're doing without AI. Yeah. So new literacies offer new and enhanced cognitive simplicities, and those can affect how. So then the question becomes, how might AI affect school mathematics? What can be learned, how it can be learned, and when? So we're going to, the other one is to look at AI as a subject of study, and we'll come back to that. Okay, so first of all, so I'm going to talk for a little bit, and then Jonathan's going to come up and talk a little bit about other things, and then we'll switch back and forth. So, so to situate these questions, what I'm going to do is give you an analogy as to what's happening in terms of another literacy, which is computer programming or computer science in mathematics education. So right now in the Ontario curriculum, in grades 1 to 9, coding and mathematics are integrated. So what is happening there? What are the potentials, and what is this reality? And before we get to that, let's step back 4,000 years and look at Babylonians and their mathematics to see how theirs are different from ours, and so we can situate that historically. So in Copilot tells us, Microsoft's Copilot, that in ancient Babylonian schools, students worked in clay tablet-filled classrooms. So etching things and doing work on that. They worked on quadratic and cubic equations. They also had used base 60, which allowed them to do a lot of work with fractions, because there are many divisors in 60. And as well, again, this is from Copilot. They also developed a much more accurate trigonometry than we typically had before we had calculators, because with base 60, they were able to create triangles with integer sides and create fractional ratios that were accurate, exact. Whereas in our base 10 system, we can't do that. So we use tables and so on, right, of decimals, approximations. So, all right, so this is what was happening then. And one more example is, here's a problem that is one of the tablets. It says, I multiplied the length and the width, area is 50. I subtracted 30 from the length and added 5 to the width, area is 50. what are the length and the width? So, so this is a familiar problem. You will find something like this in our grade 10 or maybe grade 11. You might even find it earlier using different methods. So the Babylonians would solve this using what we today call the quadratic formula. They had a version of it. They're able to solve problems. I gave it to ChatGPT to solve, and it solved it correctly. I don't think it was as elegant as it could be, and the answer wasn't simplified, but you got the correct answer. I gave it to Copilot as well. It set up the right equations at the beginning, but it eventually messed up and got the wrong answer. And it wasn't as readable, because I think it uses LaTeX, or I'm not sure how you pronounce that. Yeah. So what might happen today with coding in the grades 1 to 9 classrooms? Well, in grades 3 to 4, there are expectations about repeating patterns, and there are also expectations about variables. Students learn about variables. So what we can do is we can give students, or they can develop a piece of code easily to draw a square. And then we pose the puzzle. How could you take that square and turn it into a spiral? How would you edit this code? So, well, now this creates the need for a variable. Now, students can do brute force. They can say forward 100, turn right, forward 110, turn right, forward 120, turn right, and so on. But that does not use a loop. And if you want to edit that, it becomes really convoluted to go back and change everything. They do know that you need something in those grades that changes on the fly, but they're not sure what to do about it. So we can give them a piece of code that does that and say, oh, I found this code, and I think it solves this problem, but you take a look and see how it works, and then can you make it do those things instead? So we can create a playful environment with code where variables come to life, as opposed to being definitions or things we point to. In grades 5 and 6, they learn about conditional statements and also inequalities. So we could just as easily, very easily, with a simple Scratch program, say, take this dot, place it randomly on the screen, and if its X value is bigger than 100, stamp. So it jumps around, but it creates that image that you see up there. And then you can say to students, okay, I'm giving you that code. Look, it does that. Can you make it do this? So now you're dynamically playing with mathematics and coding in environment, as opposed to, you might have done this in the past with a number line, instead of this. In grades 8 and 9, we do, you use various structures, also use the Sumerian or Pythagorean theorem. Interestingly, the Sumerians, so there were Sumerians, Babylonians, Egyptians, they all had, the Greeks, they all had that theorem in some degree. But the Sumerians were able to find large triples. Like we can find 3, 4, 5, and you can double that and get 6, 8, and 10. But can you find one in the thousands? Well, they had those. How did they get those? And then the question comes up, well, what if I could find those and I wanted to plot them? So in grade 8, you can solve the puzzle of, can you check whether it's a triple or not? Right. So I give you two numbers, A and B. C is also an integer if those two are integers. So what you can do then is you can say, on this grid, check all the order pairs. If any of them create a C that's going to be also an integer, stamp, put a dot on it, and you get this image that you see there. All of a sudden, you see something that you've never seen before in mathematics. And you'll see all kinds of diagonals. What are those? If you look closely, you'll also see these curves curving into the origin. They happen to be parabolas. And then you can also lead to other mathematics. Where did this formula come from that they had? And it can come from different ways. One is trial and error. Another one is, well, if you have complex numbers and you square them, and A and B were integers, you're going to get C to be an integer as well. So you get into vectors and complex numbers and so on. So all of a sudden, this opens up a lot of other mathematics that you weren't even thinking about. And in grade 9, there's the concept of infinity and limit in the curriculum, and also natural density, which is a nice application of infinity and limit. And you can easily create a piece of code that checks intervals. Like, for example, let's say you want to find the natural density of odd numbers, which is 1/2, because every other number is odd. But let's say you want to check that. Check from 1 to 10 and see what it comes up. 1 to 100, 1 to 1,000. And it turns out it's going to be similar for all those. But what about the density of, let's say, the number 1? How often, if you reach into the natural numbers and pick out pick a number, what's the chance it's going to be 1? Well, between 1 and 10 will be 1 out of 10. Between 1 and 100 will be 1 out of 100. And eventually you realize that, hold on, this is like walking halfway to the door and so on. Eventually that distance, there's a limit here, yeah? So, and then if you look at square numbers, well, now all of a sudden grade 9 students are looking at something that you have infinity within infinity. So there's infinite number of square numbers, but their density is 0. How is that possible, right? So, but you can play with this with code. Yeah. So all these opportunities open up. So these coding creates a cognitive simplicities that allows us to do things that we couldn't do before. So what is happening in classrooms? One thing that's happening in classrooms is that we notice is that they use pseudocode. So this is an example that comes up regularly if you look around. So I can tell you more where I found this, but so this is a variation of what we find. So what this one does basically is this is pseudocode to determine the value of an expression. And the expression is kind of part of a linear equation. So what it does is it goes through and then tells you for certain values for m slope and y-intercept, what the value of y would be. So I can give you this in a question in a test and say, okay, read the pseudocode. What would the value of y be if you entered the value for m, this value and the other value? Now this comes under, if you look in grade 9, by the way, the Ontario curriculum 1 to 9, I think is the best curriculum I've ever seen. I mean, it does such a great job. It's not perfect. Nothing is perfect, but I think it's amazing. And read this expectation in grade 9. Apply coding skills to represent mathematical concepts and relationships dynamically and solve problems in algebra and across the strands. I love that. Like I'm empowered to do that. So, but this doesn't do that. This isn't dynamic. Even if you coded this in Python or in Scratch, it's still not dynamic. It's just going to give you an answer. You can use a calculator to solve it, so why do you need coding? So it's not dynamic. It's not really concepts and relationships. I mean, there is some algebra involved here, but it's not at the conceptual level. It's more at the computational level. So it's not coding and it's not algebra really. So, and it's something that the Babylonians can do as well. More easily because you don't have to go try to do it through pseudocode. Let me see where I am in the slides here. Oh, okay. So the question is, why is this happening? And I guess I have experiences now from the 80s in education, from the 90s, 2000, 40 years. Not because I'm that old. Dragan and I are able to time travel. That's why we've experienced these things, right, Dragan? So I've seen, changes in terms of pedagogical practices and pedagogical tools. So we went through cooperative learning, concrete materials. More recently, we have vertical whiteboards, coding, and now we have AI as well. But one pattern in all of those is that when I've had educational leaders see things and talk to me, because I've had positions where I would talk to them, they would say, it's beautiful. I love this classroom. But when I sit down with the students, the mathematics is simple and sometimes it's wrong. Or I love that they're out of the desks and working together collaboratively on the whiteboards, but the math hasn't changed. And I love that they're coding. There's so much energy in the room, but there's no mathematics happening. So these are persistent things that the mathematics, all of a sudden, the context has changed, but the mathematics hasn't. I think we have a blind spot. I think we think that if we use different or better pedagogical tools or pedagogical practices, mathematics will change. I don't think that's true. I think those tools need better mathematics, unless we bring better mathematics to it. And this is not it. I think this is a better step to it. It's not perfect, but it's better. Yeah. So, okay. So the second way of looking at AI is as a subject of study. And most educational jurisdictions right now are adding AI to the curricula. Ontario has done this in science. Other jurisdictions are. Most of the time, what they're doing at the moment is creating, looking at AI in terms of applications. You know, how you would use it, ethics of it, and so on, which is a good thing to study. The few jurisdictions that are also focusing on how AI works and how it's developed are discovering that you need to know mathematics as well. The AI that we're using today, a lot of it uses mathematical algorithms to do what to learn. So, so now we have not only that we have AI around us as a literacy that's going to be coming into schools, a number of school districts right now allowing students to use generative AI and then guiding them or helping them with that. But now we also have mathematics being coupled with this other area that we weren't aware of, which is AI. And if we teach AI, we need mathematics. How does that affect our curriculum? It changes the importance of mathematics, perhaps. It changes how the context of mathematics. So how would that affect what we study, how we learn it, and so on? And okay, so Jonathan's going to talk to us about AI and mathematics.
Yeah, so when we are talking about the mathematics of AI, so AI is a very broad term. It covers a lot of different algorithms and techniques, but modern day AI uses heavily neural networks. And so the idea of neural networks, most of you are probably somewhat familiar with neural networks and how they work, but just to go over for everybody, neural networks are basically us trying to kind of imitate the best thinking and learning device that we know of, which is the human brain. And so the human brain consists of many, many millions, billions of these cells called neurons that receive information through their kind of arms called dendrites and transmit it through axon terminals. And so you have millions of these neurons communicating with one another in the human brain. And the design of neural networks, artificial neural networks, attempts to mimic this. So you have over on the right, a neural network with the circles representing the neurons in the neural network, these artificial neurons, and the lines representing the connections between the networks, or the neurons, sorry. And in each of these individual neurons, each of these neurons basically does the same mathematical operation on its inputs and outputs a single number to every neuron that it's connected to. And in a neural network, typically you have these neurons arranged in these layers. So starting from the left to the right, you have the input layer, which takes the input information, passes it to the next layer, and then the next layer. And finally, you have the final layer called the output layer, which is then what you would interpret as the prediction of the neural network. So in the next slides, I'd like to go over kind of the mathematics of a very simple neural network. And if you aren't already familiar with the mathematics, hopefully demystify some of that mathematics, because it can be quite intimidating if you aren't familiar with it. So as part of our project at Western University, we've created this infographic that goes over the mathematics of neural networks. And in this infographic, we show how a neural network might learn to make a prediction about what digit is represented in an image. So over on the top left, you see an image of a 9 represented by an 8 by 8 grid of pixels, so 64 pixels in total. But neural networks don't necessarily work with, I mean, they work with images, but the way they interpret the images is through numbers. Everything is numbers to a neural network. And so you have to translate this image into a grid of numbers, which we do so right below. Basically, every lit pixel is a 1 and every unlit pixel is a 0. There are many other ways that you can represent images. You might be familiar. You might be able to represent it using grayscale. So rather than using zeros and ones, you represent them using a number, like a decimal number between 0 and 1 to represent the intensity of the grayness. Or you might use RGB. So you have a different number representing each of the colored channels in the image. But for simplicity, we're just going to use a very binary representation of the image. So the input layer has 64 neurons representing each of the pixels in the image. And then each of those neurons, as I said, performs a mathematical operation that we'll get into in the next slide. And it produces an output number that it then passes to every node or every neuron in the next layer. And then every neuron does its own thing in that layer, and then it passes to the next layer, and so on and so forth. The middle two layers you can see in our infographic are called a hidden layer. This is basically because the exact operation, like how it does its operation, while it is a simple mathematical operation, why kind of it does it that way is kind of hard to interpret. Neural networks are typically called black box models because we can't ask neural network, why did you do it like this? Or, why are the numbers that you're using like this? And so it can be hard to interpret, which is why they're called hidden layers. But the thing that we are interpreting is the output layer. And the output layer, we basically have it so that there are 10 neurons representing the digits 0 to 9. And basically the highest value from the neuron is basically taken as the prediction. So if the very first neuron, the topmost neuron, is the highest value of those 10 neurons, then we say that the network is predicting a 0. So this might be how a simple neural network is set up. And basically feeding the input image through the network and getting a prediction is called forward propagation. So we'll talk about the mathematics that are involved in that forward propagation. And basically it's a lot of linear algebra. So if you think of a neural network as layer-wise, you can think of the inputs to a layer as a matrix called X. And each neural network, the mathematical operation that it performs, it basically multiplies the input matrix or the input vector X by a weight matrix W. And this is just multiplying each input by a number. And then you're going to add it all together. But you're also going to add this extra value called B, the bias value. And so what you end up with, the mathematical operation, is basically the output of the layer, let's call it Y, is equal to WX plus B. And those of you might recognize it as the equation, Y equals MX plus B as the equation of a line in slope-intercept form, which is things that you teach in a secondary classroom, for example, when I learned it. But since X is not a number, but rather a vector of multiple numbers, this is a line in higher dimensions, basically. But the kind of idea of basically a linear transformation of the inputs is there. That's what each neuron is doing. The limitation of it, if we just use Y equals MX plus B, is that the network can only learn linear transformations of the input. And if many things in life are not just linear transformations of the input. So what each neuron also does is, after the Y equals WX plus B, is that it applies an activation function, F, around that output. And F basically adds this nonlinearity to the network and allows it to learn more complex relationships between input and output. But okay, so you have these weights W and these biases B, but how does the network actually learn what values these should be? And this is done through a process called backpropagation, which you can see at the bottom of this infographic, which we'll zoom in on here. So the backpropagation process involves a bit more of a complex mathematics. It involves multivariate calculus. And basically, the way you evaluate a neural network is through something called a cost function or a loss function. And this is done using statistical methods. For example, you might take the difference between the output and the expected output of the network, and then square it, so the square differences of the output and the expected values, for example, and use that as a cost function. And backpropagation will update the weights W and the biases B to minimize that cost function. So there are more than 3 weights in a typical neural network for sure. But you can imagine it in 3 dimensions, kind of at the bottom. You can imagine the surface of that cost function looking like that. And basically what backpropagation aims to do is to find the lowest point in that surface. And this is done through a process called gradient descent. But basically it's coming from calculus methods looking to find the global minimum of this function. So basically all you're doing is you're repeatedly forward propagating and back propagating to update the weights in the neural network. And that's how a network learns. I want to say it's a simple process. It can get more complex as you go on to more complicated network structures and so on, but that's the gist of it. So you might be surprised that such a simple neural network such as this is able to make predictions on images and predict the digit, and actually it can. So on our website, ai-ed.ca, we have this infographic that we just went over, as well as a Python notebook, which is an interactive environment for coding and Python, which is kind of the main language used in machine learning and data science, but that and R. But it builds and trains the simple neural network. And we also have a video to go alongside that goes over the notebook. And so here you can see a visualization of those hidden layers in the network as well as the output layer. So you can see the image there looks like a 3, and you can see that the neuron for the value 3 in the output layer is the highest value. So the prediction of the network is 3 there. So we have these resources on our websites that educators can look at and possibly share inside in their classrooms. But as a part of our project, we also have created some graphic stories on matrices, because this is kind of the core of a neural network, this data, linear algebra and matrices. So in this first story called Munchable Matrices, which you can find on our website, we have a daughter teaching her dad how to represent sales data using matrices rather than frequencies tables, as he's doing. So the data for the 2 weeks of sales are stored in 2 matrices, as you can see on the slide, and then they're added together. And she also shows her father how you can use multiplication of matrices to calculate the sales revenue there together. And so, you can go over this with students, as young as in primary school. It's a very relatable or very understandable story. And then you can also go over, what would it look like if I were to add week 3 sales, for example? What would the matrix look like? What would the size, the shape of the matrix look like? What kind of matrices can you multiply together? What kind of matrices, what kind of shapes of matrices can you add together? And so in this example, we have the week 3 sales added to a matrices to the week 1 and 2 sales. You can add those matrices of the same shape together, and then you multiply it again by the individual cost of each thing being sold to get the total revenue for the 3 weeks. So this is the kind of extensions that you can do with the story. And you can also go over what kind of, what shapes of the matrices can be added together, what shapes of matrices can be multiplied together, and why, for example. And then at the end of the story, because we want to relate it back to AI and neural networks, we can also talk. She also mentions how these are the the fundamentals to the mathematics that are used in neural networks and used in AI. And we have another story that goes over another kind of application of matrices, which are transformations. So, I mean, as I said previously, inside each neuron, you're basically doing a linear transformation of the input and then applying an activation function F to have some nonlinearity. And so this story, transformative matrices, goes over how you can interpret matrices as transformations. And so if you have a 0.35 on the Cartesian plane, what happens if you have the transformation matrix matrices shown here, for example? And so how can you interpret these matrices, for example? So for example, in the first one, you have the x value staying the same and the y value being flipped to the negative, right? And so this is a reflection in the x-axis. And then if you kind of swap which one is negative, it's a reflection in the other axis, in the y-axis. And if they're both negative, then it's a rotation around the origin, a 180-degree rotation. So again, you're still talking about matrices, but you're kind of viewing them in a different angle. And we also have a video here. I don't think you can see the video, but it's on YouTube. Basically of the animations that of what happens to the entire plane, and as well as the golden triangle, that you see what happens to the entire plane when you apply these transformation matrices. It's much more interesting to see the video of it, so I recommend going and seeing that. But can you? Oh, okay. Oh dear. Oh, it might be in the background. Would it be here? Oops. Yeah.
Should open up. It's going up.
Okay.
It's the connection. It's fine.
Yeah.
So it's going to jump off the PDF though.
Yeah.
So,
okay. Yeah. Okay. I'm sorry. It's a little slow. But you can see how you have this transformation matrix and how it transforms the plane as well as the golden triangle. And you can see how it changes everything. And these animations were created using the Manim library. If you're not familiar with the YouTube channel 3 Blue 1 Brown, they create some fantastic videos on mathematics, including on the mathematics of neural networks and how they are used in large language models, which previous speaker talked about, how they are used in ChatGPT and the transformer architecture used there. So I highly recommend checking out that YouTube channel as well. Sorry?
Go to the other tab.
This one.
And then enlarge it. Maximize the screen.
Sorry. But yeah, that's what I but yeah, those are the stories that we created, and you can find those resources as well as many other stories on AI and the mathematics of AI on our website, ai-ed.ca. All right, so I'll hand it back to George to discuss some more.
So I can find it. Is it? Oh, it's not. How do I maximize this to take the full screen here? Yeah. No, we didn't. Okay, we did. All right. All right. Thank you. Thanks, Jonathan. Yeah, Jonathan did all the coding for those simulations and also um, the uh, the networks, neural networks as well. And they're available. All the code's available online on the websites if you want to play with it or let students play with it. Okay, so what we're sharing with you is examples of how AI mathematics may be become accessible to younger students. So part of our goal here is to show you that some of this can be done, just like we did with the examples with coding. Coding allows us to do other things. This opens up another context in which to say these things around you work with this mathematics, and we can play with this in transformations in grades 5 and 6. And you can do it in a graph paper, but you can also look at it as, in financial literacy, we used this story, remember, about how you calculate the total cost, and the multiplication was not the way we do it. It's a different one. You don't cross multiply when you have two things in brackets like that. But that's exactly the way linear algebra works with matrices as well. So it's a way to bring these things in at certain times in the curriculum, even if it's not in the curriculum, as context, right? It just enlarges our view of mathematics. So you can also do this with the other part of, the mathematics that the neural networks use, which is, trying to minimize an error or trying to find the lowest point. And, this is done in TurtlePython, and the links are there for you to see, but also the code is available online. And the first one has area with constant perimeter. So if your grandmother has so much fencing and she wants to fence a garden to keep the bunnies out, what shape or should you make it so that you maximize the area of the garden, or for her pet goat or whatever? So TurtlePython would draw for you all the possible rectangles, but then also plot the area values as well. In reverse, it could be the other one, which is you have a constant area instead of. So what you're doing is you're doing relationships and concepts, right? Conceptual mathematics, just like the curriculum says, and you're linking it with coding. And you can do this like this in grade 7 and 8 for sure, but you can also do it with younger grades. So we've done these problems with in grades 3 and 4 and 2 as well, by looking at tables and chairs and then plotting the data and then joining those tops of those bars and saying, oh, what is that? It's, oh, this one opens up. And if you do this one, so you can also do for younger students, it's easier to use Python. You can use Scratch as well, but with Scratch, you have to use tables and matrix, so with Python, you can get the data right away without any extra defining any kind of lists. Anyway, so you get the data, you can plot it and see that, hey, this one opens down and so on. And how does if these were ski slopes, how are they different in different positions, and what happens at the top or at the bottom? What's the slope there? And well, and what is our answer to our problem? And where's the answer? And is that the biggest area or the low or the least perimeter and so on? So all those things connect. Those connections can be made, not because you want to teach them calculus, but it creates a context in which you can discuss these things to enrich. Just like if you're teaching language arts, you don't go into a book and blank out all the words that you don't think belong in grade 2. You leave them all in there. So we're leaving this context in there, and we're saying this is there too. Yeah. And if you wanted to plot that kind of a pattern using Python, it becomes more complex. I mean, the math itself is very similar. It's just that you have to put layers around it to plot it. And it's just kind of decoration in the end, because it's kind of all similar after that. The thing that changes is the mathematics. And then the other part is very similar once you know how to do the graphing around it. But anyway, you might do this in a higher grade. So going back to our two kind of ways of looking, not that there's only two, but looking at AI as in your literacy and looking at AI as a subject of study. we asked initially, how might AI affect school mathematics in both cases? And I think we asked the wrong question. Because I don't think AI, well, if history is a pattern, I mean, if we learn from history, just bringing in new tools or new practices into mathematics doesn't necessarily change the mathematics. It might change how you feel about it, but the level of mathematics inside doesn't change. So how should we change school mathematics now that we have this available? So at the moment, we don't have enough experience. And you had a lot of experience with it. We don't have as much, but school districts are struggling with this now. And as we build that knowledge, we should be asking what mathematics should we bring to this, not forget that part. Yeah. And everything that we shared with you is available at ai-ed.ca. All the stories are there. Everything is available, freely available. You can download the PDFs, you can share them, do whatever you want with them. And the resources are also at this link. If you have the PowerPoint, you can link that. You can click on that and get all the files all in one place. And the first file is just a quick summary, which I also have here in print, which I'll share with you. They're here, but you'll get this online as well. It shows you all the different resources that we have in PDF, and inside it also links them to curriculum expectations in a quick way. What subject areas does it fall in? It's more than just mathematics. There's also language arts, and it's all in here. And then you can decide how you want to use it or share it. And we also share with you 2 publications that are connected to the things that we talked about. And also at the top right, if you have the time, it's a quick research survey for our project. Just a couple of questions. If you answer that, we appreciate if you have the time to do that. Yeah. And so thank you again, and we'll happy to take your comments or questions. Oh, thank you.
Thank you. Thank you so much. Gardana has a question.
Thank you for your presentation. My question is maybe more related to what is happening after elementary and secondary school, because we still don't have much data on what is changed in the Ontario curriculum and actual international curricula, how that affects higher education. I'm just aware that, for example, from my experience and what I saw happening in statistics education, in higher education, we still start with mean, median, and mode. And actually in master's courses, in the 4th week, we start teaching mean, median, and mode. So my question is, when are we going to stop doing that, as you say, and changing mathematics, changing statistics, taking into account what students should have learned by now?
Mm-hmm. Yeah. So thanks, Dragana. So, we try to find, so there are a number of countries. We looked at, I think it was China and also Korea, and we try to access the curriculum because they're trying to create curricula that goes hand in hand with, but the feeling we have at this point, could be totally wrong, is that basically what they're doing is you have AI, computer science courses, and then you have mathematics courses, and you take them separately. And I'm thinking there should be something better than that. There should be some kind of integration, or at least when you're teaching this, you're doing it in the context of something else. So it's not just, you're going to learn some linear algebra over here, and eventually you'll need it over there. Maybe this year, maybe next year. And so I think we need to be smarter than that to make those kind of integrations and then adapt the curriculum. So we're actually we're not reteaching things, or we're teaching something that's at the level of the students. I feel like when I gave you that example, because I've seen those examples of pseudocode a lot, I feel like crying. I mean, the students in our classrooms, they're just day in, day out, year in, year out, they're waiting. They're waiting for something, some more mathematics, something to capture their imagination. I think we're doing it in a lot of places, but I don't think we have it as a system-wide thing. Yes.
I taught elementary. I agree with you. The issue seems to be giving context for the kids to want to learn it. And especially with math, we kind of seem to be expecting them to just absorb the mathematics without giving them a context. And my interest in the AI is, it's the training of the neural networks, which is, I guess, kind of what we're doing with kids, right? If they're not engaged in the math, they're just kind of doing it. You get to that, and I did teach some secondary too, and that's what I found. I had to go back and teach all this elementary mathematics all over again because they just didn't have a firm foundation on it. And you can't, math is a great example. You can't move on to the higher levels until you understand the basics, or the priors. I loved coding for that reason. And I would try to find little projects and challenges for them that, they create a little game or an activity, and it forced them to use that specific type of mathematics that was in that curriculum. It's going to go back to a bit of a debate too about, it's the spiraling problem. Do we go deep enough into some of the topics every year for them to actually understand it? Yes, you kind of have to reuse certain things, otherwise you forget about it. But maybe certain years we should concentrate on certain concepts. It's a teaching of mathematics question. I agree that the Ontario curriculum is fantastic. It progresses really well, but sometimes and I'm kind of getting this from students that, we kind of touched on it for a week and a half and then we dropped it. And I'll also make a comment about, who's teaching primary and intermediate mathematics. By and large, it's people who have very little interest in mathematics. And they're just kind of giving it a bit of lip service. The number of times I walk down the hallways and I've heard teachers say, well, I don't really understand fractions. And, like they kind of set their kids up, right? Not to like math. And maybe we need to relook at, how we deliver mathematics to students. And I think making it relevant, like people try to do with, some of the social studies parts and things, is what we need to do in math. I think I had a bit better luck than some of my colleagues for those reasons, right? And again, sometimes teachers don't start with answering the question why you need to use this or how do you use it. And I try to start with that, and I had a bit more buy-in. Not perfect, naturally, but so.
Thanks. Yeah. So
not a question, but
yeah. So just some quick comments on that. So I think a challenge has always been implementation. How do we change what we do? And we can't change everything at once. It's impossible. So I've worked in a lot of classrooms. I've spent, like in 1 year, I was in 18, 19 elementary schools, and I visited each school and one teacher or two teachers in that school for 5 to 8 mornings or afternoons. So about 100 visits in a year, mornings or afternoons. I loved it. I mean, I worked in grades 1 to 8. Mostly I've been working in grades 2, 3, 4. And what we try to do is focus on the mathematics itself. How can we enrich the mathematics concepts? Where is the structure of mathematics? And how do you structure the structure in a way that offers some kind of mathematical surprise and insight? So this is the kind of work we've been doing. And I think we don't have to change everything at once. If we can do some of those things occasionally, once every unit, once every other unit, start small and do it well, I think it gives us a different view of what mathematics is. And I mean, having worked with teachers that are very young, I mean, they're open to all these ideas. So at first, I was connected to their curriculum, but then after the first time, they say, "Do you have anything else like this?" So it's we are all thirsting for better mathematics, teachers and students. We need to see samples of it.
Thank you very much. Hi, thank you for the talk. There was a lot of deep discussions here, so I have a very dumb question comparatively. You showed us some examples of teaching mathematics with programming, but my question is, was there an example where the students were using AI or interacting with AI in any of the examples that you showed? I couldn't follow along maybe, but.
So no, we didn't share any examples of that. I do have a course that's coming up in the summer at the university level, where I'm opening up to students to use generative AI fully in that course. And we don't have examples of that yet. School districts are just starting to use some of these tools. So what we presented was kind of the historical point of view. Here's what's happened in the past. So to say that we can't assume that AI is going to make things better in terms of mathematics itself as a subject, as something worthy of attention. And so as a caution, yeah. So yes, so the answer is no, we haven't shared any examples. Yeah. Yes.
My big question is, in this modern world and going forward, how do we know what students need to know? So I think back to elementary school where I was taught how to find a square root manually. I guess it could be argued I learned problem solving. No one will ever have to do this manually again. The calculator will always get it right. Eventually, AI will get the answer all the time. I'm all about problem solving. But at what point do I decide what I'm teaching now is the modern day equivalent of teaching people to manually find a square root? This is a big philosophical question. I love math, and I love math for math's sake. And, eventually, how much, I don't know, reducing an algebraic expression needs to be done, ever. This is from someone who loves math. So could you answer that in 10 sentences or less?
No, I don't know that I can answer it. I mean, I have to go off on a tangent to be able to comment on it. I mean, what I would say is many years ago when I started in education, I came across, my supervisor was Gila Hanna, and she brought in speakers, and one of them was Peter Taylor. And I mean, he posed he told the story of, working with his colleague Bill Barnes, who taught poetry. So they had math and poetry class. And he said, I went to his class and he was passionate about what he was teaching about. But he said, I didn't feel the same passion about the math that I'm teaching to my students. And he's passionate about mathematics. So he said, he's like, that question that he asked, how do I bring something that I think is worthy of my thinking, anybody's thinking mathematically? So that's the big puzzle. I mean, I don't want to blame Peter for all the mistakes I made, but that was
online, actually.
okay, Peter. But Peter, so if you're there, thanks for that, because that's kind of been one of the, that resonates with me since for many years now, decades, and I've been struggling to find the answer. So I think that's the puzzle we need to solve occasionally in our teaching, in our curriculum implementation. We need to find those things that are worth doing. It's just like a good movie, at points you're like, you surprised, you get new insights and so on. And this can be the same thing in the classroom, but it doesn't happen every day. Like the whole movie isn't just all surprises. It's just, there's other things happening as well. I don't think I answer your question directly.
I was surprised, not surprised, I was happy to see in your presentation that you went back all the way to the Babylonians, and perhaps we can make that connection with the Egyptians as well. And from the conversation from other colleagues, this idea that mathematics is cumulative, that you have to take one step before taking another step. I'm wondering on your thoughts of going back to how the Babylonians and the Egyptians sort of educated their students or the people who had access to this kind of knowledge, because they worked on very specific problems of their context at the time. So when you presented, for example, that they were dealing with quadratic functions or quadratic equations, they were not actually equations. They were represented as problems of their everyday life in that area. And I've been reflecting about that from the angle of financial literacy, which is the research that I do. And I'm starting to think, and I'm wondering your thoughts on that. If we taught mathematics through pressing issues or pressing problems that we have in our society nowadays, if that wouldn't allow us to be less cumulative, so less dependent on steps that are taken every grade, and we would potentially allow students to approach mathematics through different angles, through different perspectives, and through different points in their life as well. Because otherwise, we are just losing them in this pipeline until nobody comes to STEM majors or things like that. I'm wondering if, from your experience in this kind of research, if that would be possible to approach math through problems that we encounter in our life, and how we could model or solve or make sense of these problems.
Yeah, so mathematics grows through applications, and it grows through itself as well. I mean, just by doing mathematics studying. So both are important. And if you can contextualize that for students, if you can provide real world context, it helps. And at the same time, within mathematics, we can provide contexts. I mean, there's ways. I mean, we've done work with infinity and limit, trigonometry, circular functions, group theory in grades 2 and 3 in ways that are accessible to young students. So we're able to talk about it without even talking about it that way. And so we're able to create views of mathematics that have a low floor and a high ceiling. So I can talk about it to somebody that doesn't have a knowledge of mathematics and communicate with them, but also it's still open. So that's within mathematics. But then can you do that also within the society as well? So I think both are valuable. My focus has been within mathematics. Okay? The other one is very important as well.
George, just I think a question for me, and probably very selfish in nature. I agree with you. The grade 1 to 9 curriculum is a great curriculum. It flows well from 1 to 9 with the same 5 strands and so on. But I guess my question is, what about 10 to 12? Do you have any sense of, because it doesn't align, it is now almost 20 years old in Ontario. And then I think it also leads to some of the issues like Dragana was mentioning, post-secondary, and some of the issues we're seeing there. So do you have any sense of if some of the changes that happen in 1 to 9 will be reflected in maybe a coming curriculum change in 10 to 12?
Yeah, so I mean, a lot of us have been involved with, Dragana, and others have been involved with the curriculum and trying to help and support, but we don't know. I personally, maybe Dragana might know. I don't know what's happening next. I imagine that we'll be revising all of that curricula because it's been a long time, and all students are coming in with different skill sets as well, so you need to adapt. So I think hopefully the same thing will happen. Yeah.
Maybe we'll give it one more question, the last question, if that's okay.
I have a question.
Sure.
So I just want to ask Jonathan, I mean, any reflections on any comments, because you study mathematics and you study computer science and you work in artificial intelligence, and you were a student as well on one point. We've talked about a number of things here. Anything stick out in your head in terms of
I mean,
Something you want to comment
yeah,
on?
so my experience, obviously, it's not as an educator. I'm not a teacher. I don't teach students or anything. It's just as a PhD student. But like a lot of the questions that have been asked, definitely I can relate to. Like on the topic of, you teach one thing one year and then maybe later on you're introducing the exact same concepts. That's what happens, right? Like how many times has it been where I've learned a concept, crammed for it for a final exam, and as soon as the exam's over, completely out. Like that's probably not the best way to do things, right? Like if I had maybe some better understanding or some context to what I was learning, then maybe it would stick with me more. So those are the challenges I think that is presented to educators, is how to adapt things and change things so that like asking students, what do you want to learn today? Like, and how can I, take that what you want to learn and then, add some mathematics to it. Do you want to just play, video games or like Fortnite? Can I present mathematical concepts, within the context of Fortnite or whatever they want or interested in? And like, I don't know, it's hard, but I think it's definitely rewarding to the students if it can be managed. But yeah.
So I have two questions. First one is that I have experienced that AI gives answer correct, but the steps it gives, sometimes it is complicated. So AI gives answer. If I ask AI that give me answer of a simple basic question, then AI will complicate the steps and then they will give the answer. So why is this? I mean, the steps are really complicated. You don't understand the steps. So why is this like?
Are you asking why you're asking an AI to explain something and it's giving you complicated steps, or are you asking why AI is
I mean,
complicated?
AI is giving answers by complicating the steps. So AI knows the formulas, but why sometimes it gives the incorrect formula and complicates the steps. Sometimes AI confuses itself. That's why.
Yeah, I don't have a good answer to that. I think like if you're talking about like ChatGPT on why it gives complicated responses, I think it's just the result of the language model. It's just trying to give you something that sounds correct, and sometimes it is correct, and nowadays more and more it is correct. But maybe the complicated language that it uses, is more seemingly correct. Maybe that's why it's giving you more complicated answers for incorrect formulas. But maybe if you ask it like, can you explain it in a more simple manner, maybe it's successful in doing that. I don't know. But yeah, I think as far as the language that ChatGPT and stuff uses, it's just a result of how the language model was trained, I think. I'm not sure if that answers your question, but.
Thank you so much.
Thank you.
Thank you. Wonderful.